So hello everyone, welcome to another video on Internet of Things. In this video we are going to start a new module, and there are three topics in this module. One is this data handling and analytics. The next topic would be cloud computing, and the third topic would be sensor cloud. So let us start with the first topic, that is your data handling and analytics. Alright, so before we talk about this data handling and what is data analysis, let us look at one use case. Alright, so IBM has this advanced metering system. It's a digital meter to look at how much electricity is being consumed. We have meters at our home, but ours are not smart meter yet. Alright, as far as I know, there are people in APTCL who are working towards building smart meters, but right now we don't have. Anyway, IBM has a solution, that is advanced metering system, and this is used by a company called Encore. Encore is a utility company, electricity company in USA, and I believe it's the largest electricity company in Texas. Alright, and they have around 2.5 million users. So the thing is that this IBM advanced metering system, it updates, does a reading, it updates the reading in Encore's server once every 15 minutes. So usually what happens, our meters, our APTCL, they come and check the meter once every month. So compare that to once every 15 minutes, right? So now your meter is being read 3000 times per month, not just one time per month, right? Previously meters were being read one time per month, now it is being read 3000 times per month. So now with this lots of analysis can be done. So things like now the company can analyze when there is less load on the network, so on the grid. So at that time the company can tell the user that after 11 PM there is less load on the grid, you can use your washing machine after 11 PM. Alright, so that will affect the grid less, and then they can do this kind of thing. They can create billing that has variable billing. So right, they can incentivize industries to run at low load time. Alright, so that way industries will run at time when the load demand on the grid is low, and that would further decrease the load on the grid. So this kind of analysis can be done, this kind of things were done by Encore using IBM's advanced metering system, right? And then they allow you to create this home area network using Zigbee's smart energy devices, and then you can analyze how much electricity is being used by various devices in your home, and how do you reduce the consumption even further. So those kind of analysis also you can do, right? So that is what IBM's advanced metering system gives you. Now my point here is this 2.5 million users using this IBM's advanced metering system, they will generate 240 million data points every day. Okay, 240 million data points every day. This is a huge amount of data. Alright, this is an analysis that is done by IDC Global Datasphere back in November 2008. They have done this analysis that by 2025 annual data generation from IoT and other devices would be equal to 175 zettabytes. This is a very big amount of data that needs to be stored, that will need to be analyzed. Okay, if you want to use this data for various type of tasks, then you have to use this data, you have to analyze this data. So in order to analyze this data, you have to bring the data, you have to first store the data on some hard drive, and then you have to read the data from the hard drive. You have to bring the data from the hard drive to the processor, and then you need to run some algorithm on this processor, right? So there is this thing. Now we will talk about this field of study called big data. Big data is a field that treats way to analyze, systematically extract information from and otherwise deals with data set that are too large or complex to be dealt with by traditional data processing application software. Big data challenges include capturing data, data storage, data analysis, searching, sharing, transferring data, visualization, querying, updating, privacy, and what are the data source, handling those data source. So we will be looking at this topic called big data. So big data essentially deals with large data. So large in the sense that you cannot store this data on a single computer. All right, so maybe you have 5 TB of data, and your computer you have several computers, each of them has 1 TB. So now you can do one thing, you can split this 5 TB data into 1 TB and then store in these 5 different computers, right? So that is one thing that you can do. And then once you have stored, the game does not get over there. You have to read this data and then you have to analyze this data. So lots of things, you have to process this data, lots of things needs to be done. So big data is a field that studies how to handle this type of large data, how to process this type of large data, and we will be looking at this in this video. Alright, so there are different types of data. Your data may be structured data, for example the data that is in your database. So in your database you have data that has schema associated with it, right? So you can look at a table in your database and you will know what is the type of data, what is the meaning of data in one column. All right, so that would be given by your schema. Now compare that to semi-structured data, for example XML or JSON, for example email or web pages. In email, okay, for example if you look at the to field, you will know this contains a email address. If you look at CC or BCC field, you will know this contain email address. If you look at the subject field, you will know this has a summary of what is in the body field. All right, so yes, your data is separated into different fields, like you have to CC, BCC, subject, body. So you have all these things, but then inside this body you have this big text, all right, which is now unstructured. So this text will be in natural language that you cannot analyze, that you cannot read this properly. It will be a blob of character. So you have this problem that although your data is structured into fields, but within these fields your data is unstructured. So this is a semi-structured form of data. Similarly in JSON or XML, you may have some JSON variable. In that you may have a large blob of text. Okay, you may have this image that is base 64 encoded, you may have inside XML, right? So your image, you can convert it into text and you can have that inside an XML. So that would be unstructured, right? So similarly your web pages is structured using some web page schema, using some XML schema that is given to us by W3C. So we have some structure, but then you may have some div, and inside that div you will have lots of text. Now this text itself would be unstructured, right? So these are semi-structured. You have some structure, but within that you have unstructured things. So you cannot save an XML directly into a table, right? So you have that problem. It does not have a complete proper schema like a database table. So compare that once again with unstructured, that are completely unstructured. For example, your media files, that is your music, video, images. So these do not have a proper schema. Then your natural languages, your documents that you have. So these are unstructured. So these are a different type of data that may be given to a this system, this big data system will need to store this different type of data, right? So this is what you have. Now big data is characterized by these different V's. These are called the different V's, the 5 V's. So what is the volume? So your data will be a large volume. So what is the volume? That is the first thing that needs to be considered. Then what is the variety? How much variety is in the data? How much different is one data from the next data? My first data might be some text. The next data that needs to be stored might be some image. So that would give rise to a variety in data. Then velocity. What is the rate at which data is arriving? Alright. Then veracity. Veracity is what is the quality of data. Alright. Is how useful. What is the value of the data? So value once again is one more V. So what is the utility? How useful is the data? And then veracity is what is the quality of the data? Alright. So these are the 5 V's that are characteristic of big data. Alright. So I want you to look at this graph. Observe one thing, that the space, okay, the capacity of hard drive is increasing rapidly. Alright, but then the transfer rate of hard drive is not increasing at that rate. The transfer rate is fairly constant. So what is the problem? Today you have a 1 GB hard drive, tomorrow you may have a 30 GB hard drive, but then the rate at which you are reading this 1 GB, okay, is still the same. So although your hard drive now you can store 30 GB, you will need 30 times more time to read the entire hard disk. Previously, if you needed 1 hour to read the entire hard disk, now you would need 30 hours to read the entire hard disk, because the rate at which you read data, that is not increasing. So you have this ability that you can store as much data as you want. Your hard drive is getting bigger, so you can dump lots of data into your hard drive, you can store lots of data in your hard drive, but then when you read this data, you will need lots of time. Okay, so say you had 5 different hard drive, okay, and each of them will transfer 1 GB in 1 hour. Okay, so if you stored your data in 5 different hard drives and you read from all these hard drives parallelly, you would be able to read the entire 5 GB of data in 1 hour, right? Since you are reading parallelly. Compare that to if you are reading from one hard drive. If you had your entire 5 GB of data in one hard drive, you can read 1 GB in 1 hour, then you would need 5 hours to read the entire 5 GB of data from one hard drive, right? So although you have the capability to store large amount of data, but then the problem remains that you will need larger amount of time to read this large amount of data. Okay, so remember this problem. This is a problem that we have, that although our hard disk capacity is increasing, the transfer rate is fairly staying the same. Now yes, new technologies are coming in, things like SSDs are coming in, but then we are not concerned with SSD. We are not talking about SSD right now. They are very expensive. We cannot use SSD in data center. Alright, your SSD might be your primary hard disk where you store your games, where you store your operating system in your laptop or your PC, right? But it is not the type of hard disk that will be used in data center to store TB or zettabyte of data. So SSD is not a solution yet. The price is too much, right? So we are talking about our normal magnetic hard disk that we have, the one that spins around. All right, so one more thing, the data is increasing. We have very big data, but then the cost of hard drive is decreasing. All right, so we don't need to worry about space. So we will always have space to store as much data as we want, because the cost is decreasing. We don't need to worry about the cost of storing data. The thing that we should worry about is the speed at which we can read and write the data, and the speed at which we can process this data. Okay, that is our thing that we should concentrate on, not the cost of storing data, since our hard drive cost is decreasing. I want you to look at this one example. Say 1 TB data is stored on a PC with 4 IO channels with 100 Mbps data transfer speed. Okay, so this would need 42 minutes to read the 1 TB data. So instead, if we distribute and store this 1 TB data on 10 different PC, okay, so previously from one PC it needed 42 minutes. If we have 10 different PC, it would need 4.2 minutes. Okay, so by distributing our data to lots of different computers, we can speed up the rate at which we can read this data, or we can process this data. So we have one tool, it is Apache Hadoop. So Apache Hadoop is based on a few papers that was published by Google. So Google had this distributed file system and then the Mapreduce algorithm. Alright, so they published paper about this, and they made their algorithms open source, their file system open source, and then these people, this Apache's Hadoop group, they implemented this paper on their own in a open source software. So Apache Hadoop is a collection of open source software utilities that facilitate using a network of many computers to solve problem involving massive amount of data and computation. Originally designed for computer cluster built from commodity hardware, it has been found it has also found use on cluster of high-end hardware. All the modules in Hadoop are designed with the fundamental assumption that hardware failures are common occurrence and should be automatically handled by the framework. So yeah, Apache Hadoop is a software that handles big data. Alright, so Apache Hadoop was initially developed with this view that lots of commodity computer, lots of normal computer that we can buy in normal shop, okay, we will purchase those computers, and then this collection of computer we will use together as a cluster. Alright, and then this cluster will work as one high-end computer, right? So all our data we will distribute among these different commodity computer. But then nowadays, even high-end computer, all this server rack computer with Xeon processor, for example, 32 GB RAM, and TBs and TVs of storage, so those kind of computer are also running Apache Hadoop. But then, although high-end computers are running Apache Hadoop, but then the aim was that even low-end computer will be brought together, and then all these small computers, all this low-end computer together, they will give me a high processing distributed system, and the system will be high processing when I combine all of this low processing computer together. Alright, so one assumption that Hadoop makes is that lots of computers, these computers being commodity, will fail, and so Hadoop has to handle this failure on its own automatically. So that is one more thing that Hadoop does. Alright, so there are four main parts of Hadoop. Apart from this, there are lots of other things in Hadoop, but we will be looking at only two important things out of these four. So what are these four? Hadoop Common. So these are all the libraries and utilities that are needed by other modules in Hadoop. Okay, then we have HDFS, Hadoop Distributed File System. So this is a file system that stores data on machine and providing a very high aggregate bandwidth across the cluster. So it is the file system. Now when we look at HDFS file system will be distributed across several computers. Okay, so when I store file in this HDFS, my file will actually be stored in several computers, but I will be looking as if when I look at this file system, it will appear as if my file is just there. I have this one file, my data of the file is distributed across many computers, but it will appear to me as one file. I can read the file, I can add to the file, I can do things that I can do in our normal file system, right? So this is distributed file system that will work across a cluster of computer. Then we have Hadoop Yarn. Yarn is the management software that will manage these different clusters and will manage the different application, the scheduling type of the application. All these things will be done by Yarn. Okay, and then we have Mapreduce. So Mapreduce is a programming paradigm. We will be looking at Mapreduce. So Mapreduce will do what? It will take your computation. Previously our computation was in one PC. Okay, so if I needed to analyze something, our entire analysis will run on one PC. Now this analysis will be distributed. Okay, so analysis is distributed. Some partial analysis will be done in lots of different PC, and we will get back the result, and then we will have this complete analysis by combining this partial analysis. So this paradigm of programming, this is called Mapreduce, and we will be looking at that. All right. So the first thing, Hdfs. Hdfs has a master-slave architecture. A Hdfs cluster consists of a single name node, okay, which is a master node that manages the file system namespace and regulates access to files by clients. Then apart from that, there are a number of data nodes, usually one per node in the cluster, which manages storage attached to the node that they run on. So we have two different type of node. All right, one is the master node and the other is the slave node. So the master node will run this daemon, this software called name node. Okay, name node is responsible for managing all the meta information about all the files. All right, so all the entire file system will be managed by name node. Name node itself will not store any data. The data will be stored in the slave node. All right, slave node will run this software, run this daemon called data node. Data node will be responsible for actually storing the data. So we have different computers, a cluster of computer. One of this computer will be the master, the rest of them will be slave. The master will run a software called name node. The slave will run a software called data node. The name node will be responsible for storing all the information about all the files that are stored. The file themselves will not be stored in name node, the files will be stored in data node. So data node will be responsible for storing the files. Okay, all right, so we have this architecture. We have this master node, slave node, that is your name node, data node architecture. Okay, next I want you to look at this picture. This is the picture of a data center. Okay, so in a data center we have different racks, and in each of this rack we have lots of computers. All these that you can see are computer. All right, they have processor, they have RAM, they have storage. All right, and then there is a motherboard that will connect this storage, RAM and processor. So usually these are very high-end PCs. It will have processor like your Xeon processor, very large amount of RAM and a large amount of storage. So these are very high-end computer. These are no different from the normal computer that you use. Usually we have our desktop one form factor where we have a cabinet, a CPU that is cubic, and we store it in this way on our table. Here it is just a different form factor. Okay, there is no other difference, just it looks different. It will run your operating system like Linux, Windows, whatever you want to run. So it will run your normal operating system. It's a normal computer. All right, so each of them is a computer, and there are lots of computer in a rack, and there are lots of racks. Okay, so this is what a data center looks like. Okay, with this knowledge, let us go back and look at our Hadoop cluster once more. Hadoop cluster will once again contain different racks. In all these racks we will have different computers. One of this computer will be name node. There will be another computer that will be a job tracker. Okay, job tracker will track all these different applications that are running, different jobs that are running in all the different nodes. Then apart from name node, job tracker, there will be a secondary name node. We will talk about that. And apart from that, we will have lots of data node. These are our slave nodes, right? Slave machines. So within one rack, we will have a rack switch that will be used to communicate among the different computers that are in a rack. And then apart from rack switch, there will be core switches that will be used to communicate between different racks. All right, and then together all this will form our Hadoop cluster. Okay, so this is what we have. Hold on. All right, sorry. So this is what a Hadoop cluster looks like if we look at it from this rack perspective, right? So there will be lots of racks, and the racks will have a switch, that is a rack switch, that will do what? That will do this communication between the computers in a rack, and then between two different racks the communication will take place through these core switches, these high level switches. All right, so this is what we have. Now what is a name node? Name node will manage your data node. Then there are two files essentially that name nodes has to manage. These are your FS image, the image of the file system. Alright, then the edit logs. Whatever changes we made to FS image are recorded in edit logs. Then it record changes that take place to the file system. Okay, if something is deleted, if something is added, that will be recorded in edit log. Then it regularly receive heartbeat from data nodes. Alright, so it will regularly see if the data nodes are active. So this usually take place once every 3 seconds, I believe. It keep a record of all the blocks in HDFS. So all the blocks, we will talk about what is a block very soon. So it keeps a record of where all the files are stored and all the metadata about the files. So we have these different files. Files will be stored in lots of places, right? So name node will know where my file is. If my file is very big, then it will be distributed across 2 different computers. So my name node will know what are the different computers where my file is distributed. Alright, so name node is also responsible for managing the replication factor. Once again, we will talk about replication factor very soon. And in case data node fail, name node chooses new data node, and what are the new data nodes that will be used? It will replicate data from some backup to this new data node, and then it will balance these uses and communication traffic among the data node. So name node is essentially the master that will keep track of the metadata, keep track of all the edits that is happening. It will look at whether all the data nodes are alive and working, and then it will keep track of way to replicate this different how to replicate this data. All right, and then it will manage disk utility and then communication among all these data nodes. So this is essentially the function of name node. Then we have slave node. Okay, so slave node, they actually store the data. Name node stores the metadata, slave node will store the data. Okay, they perform low level read and write request into the file system, and then periodically they will inform the name node that they are alive once every 3 seconds by default. Alright, so this is data node. Apart from this, we have secondary name node. Don't confuse secondary name node with backup name node. Okay, secondary name node is not name node, it is a helper to the name node. So it will do what? It will read all the data from name node, all the metadata from the RAM of the name node, and write it to hard disk periodically. Okay, so it will query for edit logs in name node, and it will write all the edit that has happened into the FS image. FS image contain the image of the file system. So it will put this FS image edit into the FS image, and then the secondary name node will copy this to the name node. Alright, this copy this updated FS image back to name node. So this is what a secondary name node has to do. Don't think that secondary name node will act as name node when the main name node goes down. That is not what is happening. Secondary name node has different function. It has to offload some of the working from the name node. Especially it has to write down this edit that has happened back into FS image and put back the FS image into the name node. Okay, so this is what secondary name node does. Alright, now back when we were talking about name node, we were talking about where all the blocks are located. So what does block mean? If say my block size is 128 MB, then what will happen? If I have a file of 256 MB, it will be broken down into 2 files of 128 MB and 128 MB. If say I have a file size of 200 MB, it will be broken down into a file size of block size of 128 MB and 72 MB. If it is less than 128 MB, it will remain one block. Say I have a big file, okay, of 400 MB. This one, it will be broken down into 4 blocks. The first 3 block will be 128 MB, the final block will be 16 MB. So this is what Hadoop does. Hadoop will do what? it will take a block, it will take a file, and it will have some block size. Here my block size is defined as 128 MB. In Hadoop version 2, the default block size is 128 MB. In version 1, it was 64 MB. Alright, so Hadoop will do what? It will divide the file if it is greater than the block size. If the file is less than the block size, then there is no question of dividing. Alright, now if my file is greater than my block size, the file will be broken down into different blocks, and these blocks will be stored in the different data nodes. Alright, now why, you may ask, why is it that my block size is 128 MB? Why not something less like 4 KB? Okay, if I have very small block size, say 4 KB, then what will happen? One big file will be split into lots of different small files, right? So if I have very small, the number of blocks for a file will be very large, and so I will need to store information about where all these blocks are stored. So this will be stored in the metadata. Okay, so the metadata about all the files will become very large, and the name node will not be able to handle this large amount of metadata. Okay, so our block size is comparatively larger, 128 MB. Okay, why is it not very large? Why is it not 1 TB? Then once again that problem arises. We will need lots of time to read this 1 TB. Reading 128 MB is faster. Alright, now dividing files into blocks is important because of one more reason. Let's say my commodity hardware, I am making a cluster with commodity hardware. Say all my PCs have 500 GB storage. If I need to store a 2 TB file, okay, all my PCs are 500 GB, I have a 2 TB file that I need to store. If I don't divide my file, then there is no way I can store my file in any of the PCs, right? What is the way to store? My big file will be divided into blocks, and all these blocks will be stored in different PCs. Alright, so this is what will happen. Say I have some file, and that file is divided into different parts. Alright, so say it is divided into 5 parts. Now these 5 parts will be stored in lots of different data nodes. Say part 1 and 2 is stored here, part 3 is stored here, part 4 is stored here, part 5 is stored here. Alright, so apart from storing, there is one more thing that is going to happen. Our blocks are going to be replicated. Say block 2 is stored here, block 2 is also stored here. Okay, block 3 is stored here, block 3 is stored here, and block 3 will be stored in one more place. Say, hold on, so here, and it will be stored in some other place also, right? Okay, it is not shown. Okay, so what will happen? Look at this block replication. This is our metadata. I have this part 0, it is replicated 2 times, so it will be stored in block 1 and block 3. Our part 1 is replicated 3 times. It is stored in block 2, it is stored in data node 2, 3, 5. Okay, so yeah, remember this, my file is going to be replicated. Why is it going to be replicated? It is going to be replicated because of this reason, that I am using commodity hardware, and my commodity hardware can fail at any time. Okay, if say I am storing this block 1 in only one PC without replication, then what will happen? If that PC fails, I will be unable to access, right? Now with replication, Hadoop will automatically fall back and use the second block instead of the primary block to read the data. Okay, so this is block replication. Our block will be replicated in different data node. Okay, so my file will be divided into different blocks. My blocks will be stored in more than one PC. So if my file is divided into 3 blocks, so these 3 blocks will be scattered around different data nodes, and each of these block will be replicated in other data nodes. So there is lots of redundancy built, so that if one PC fails, there is still chances that we can access the data from some other PC. Okay, now the way this block is replicated is taken is taken place with a rack-aware replication algorithm. So it is a replication algorithm that is aware of the fact that my data is stored in data node, and these data nodes are arranged in racks. Okay, so we already talked about how in data center these computers are arranged in racks. So our replication algorithm, this block replication algorithm, it is aware of how these computers are divided into different racks. So what will happen? My first block, say, is put in this rack. My second and third replicated block, okay, this is my original copy, this is the replicated copy, these two are put in some other block. So say this is my red block, so red block, first one is put here, second one and third one over here. I am putting, say, blue block, first one is put here, second and third are in some other block. So one replica is on local node, second replica is on a remote rack, third replica is in the same remote rack. Okay, apart from that, additional replicas are placed randomly. So now why is it replicated across different rack? So that if one entire rack fails because of some power issue, okay, for example, so if an entire rack fails, then at least my data will be available in some other rack. Now why is it that two of the replicated blocks are in the same rack? So see, from here replicating to this rack, we will have to go through the core switch, alright, but from replicating from here to here, we will have to just go through the rack switch. So replicating from one rack to another is costly compared to replicating within the same rack. Now because of this, our replication, we have one in our original machine, two in our different machine. Now the probability that two of the racks will fail is lesser than the probability that one rack will fail. Okay, so two racks will fail, we think that is not going to happen. So two are in one machine, one is in another machine. So even if one rack fail, in some other machine we will have, in some other rack there will be a computer in which we will have our block. Alright, so this is what we have. Okay, so with that, let us look at the Hdfs architecture once again. We have this name node. Some name node will contain all these different metadata. So metadata itself is data, so it may be once again placed in some data node. We have this different data node in one rack, we have this data node in another rack. So data node is replicated, data blocks are replicated, block operation may be done. Some client may be name node will be doing some block operation. Some client may be writing data to the different data nodes. Some client may be reading metadata from the data nodes. Alright, so this is a architecture of Hdfs. Okay, now in order to write data into Hdfs, this is going to happen. First, our client, our Hdfs client is going to run in some JVM, okay, Java virtual machine, in our client machine, client node. So our Hdfs client is going to write some file. Okay, it is going to write, say, block A of some file. So what will happen? First, it will send a request to the name node that I want to write block A. Name node will send it a list of IP address of the data node, say data node 1, 4 and 6. So name node knows that replication factor is 3. So the block A is going to be replicated 3 times. So in 3 different machine, name node will give you the address of first machine which will be in one rack and address of 2 different machine which will be in some other rack. So first a write request is made, then name node will give IP address, then through number 3 the data will be sent to core switch. Number 4, the data will be returned to data node 1. Okay, so number 4 data is returned to data node 1. Then number 5, data node 1 will write the data to data node 4. Okay, client is not going to write to data node 4, data node 1 will write to data node 4, and then data node 4 will write to data node 6. Okay, this is not right. I am sorry, first a write request is made, then a IP address are sent, then client node is asking if data node 1 is ready. Okay, so client node is asking if data node 1 is ready, data node 1 will ask if data node 4 is ready, then data node 4 will ask if data node 6 is ready. Alright, so first we have to set up this pipeline. Okay, next we will come to write. First we have to set up the pipeline. So client is getting the list of IP address where it will write, then it is asking all these different data nodes whether they are ready to be written to. Okay, so remember this, client will not ask all these different data nodes simultaneously. Client will ask data node 1, data node 1 will ask the next data node, and then that will ask the next data node. Alright, so after that is done, after the ready message is sent, the acknowledgement will be sent that yes, I am ready. So client data node 6 will send to data node 4, data node 4 will send to data node 1, and data node 1 will send to the client machine that yes, I am ready to write data, you can now send me data. So this is how we set up the pipeline to write data. Once the pipeline is set up, this is how the actual data, hold on, yeah, this is how the actual data is written. Alright, so first we have to write to the core switch. Through the core switch we write to data node 1. Okay, so we write only to data node 1, then data node 1 will write to data node 4, and data node 4 will write to data node 6. So once we write to data node 1, the data will be available in data node 1. Data node 1 will replicate this in data node 4 through the core switch. Now from data node 4 to data node 6, it will be directly sent through the rack switch. So this replication is done by data node themselves. Client does not necessarily need to write to all these three, okay, data nodes. So client will not write to the three data nodes. Data node, only one data node will be written to by the client, and that data node will copy the data, will replicate the data to the other data node. So number 1, client sends the data to core switch, and through the core switch to data node 1. Then number 3 to data node 4, number 4 to data node switch. Then after the write is done, data node 6 will send an acknowledgement to data node 4, data node 4 will send an acknowledgement to data node 1, and then the data node 1 through the core switch will send an acknowledgement to the client. Alright, that yes, the writing is complete. Now data node 6, then the client will inform the name node that the writing is complete, and the name node will update the metadata as necessary. So that is, after that the metadata will be updated, and then the pipeline will be closed. So all this TCP connection will be closed. So all this data transfer, they took place through TCP IP through this pipeline. Alright, so this is what happens. So I have so let me read out all these things. At first the HDFS client will reach out to the name node for a write request against 2 blocks. I give an example of 1 block, it can use 2 blocks, not a problem. So 2 blocks, say A and B. The name node will grant the client the write permission and will provide the list of IP addresses of the data node whether the file blocks will be copied eventually. So it will send the IP addresses. The selection of IP addresses of data node is purely randomized based on availability, replication factor, and rack awareness. So randomly it will send this IP address where to put this data. Alright, where to put all these different blocks. So based on how many IP addresses will be sent, it will be based on replication factor, and then where are all these different machines, so that will be based on rack aware algorithm, and then apart from that randomly it will send this IP packet constrained by randomly, but still constrained by rack aware algorithm and replication factor. Okay, so let's say the replication factor is set to default, that is 3. Therefore for each block the name node will provide a list of 3 IP addresses of data nodes. Okay, the list will be unique for each block. Suppose the IP addresses are this: IP addresses of data node 1, data node 4, and data node 6. So 1, 4, and 6 is sent, say for block A. Then each block will be copied in 3 different data nodes to maintain the replication factor consistent throughout the cluster. So 3 process, we set up the pipeline like this. Then after pipeline, we actually write the data in this way, and then once the data is written, then we shut down the pipeline after the acknowledgement is done. Okay, so the 3 steps. So the client will choose the first data node in the list, which is data node 1, and establish a TCP/IP connection. So in our list that is sent to us, the first data node is data node 1. So with that, the client will set up a TCP/IP connection. The client will inform data node 1 to be ready to receive the block. It will also provide the IP of the next 2 data block to the data node 1 where the block is supposed to be replicated. Data node 1 will connect to data node 4. Data node 1 will inform data node 4 to be ready to receive the block and will give it the IP of data node 6. Then data node 4 will tell data node 6 to be ready to receive the data. Okay. Then the acknowledgement of readiness will follow the reverse sequence, that is 6 will inform 4 and then 4 will inform 1, as already explained. At last, data node 1 will inform the client that all the data nodes are ready and a pipeline will be formed between the client, data node 1, 4 and 6. So ready is done and then the pipeline will be formed. Now the pipeline is complete and the client will finally begin the data copy or streaming process. As the data pipeline has been created, the client will push the data into the pipeline. The client will copy the block to data node 1 only. The replication is always done by data node sequentially. So replication will be done one after another sequentially by the data node. Original copy will be placed in the first data node, then the replication will be done by the data node. Alright. Once the block has been written to data node 1 by the client, data node 1 will connect to data node 4. Then data node 1 will push the block in the pipeline and data will be copied to data node 4. Okay. Again data node 4 will connect to data node 6 and will copy the last replica of the block. Once the block has been copied into all the 3 data nodes, a series of acknowledgement will take place to ensure the client and name nodes that the data has been written successfully. Then the client will finally close the pipeline to end the TCP session. Okay. So once the block is written, we will have this 4, 5, 6, 7, 8, 9. So these are acknowledgement that write is complete successfully. So after this is done, name node will update the metadata and close all this TCP connection that we have. Alright. So the acknowledgement happens in the reverse sequence, that is from data node 6 to 4 to 1. Finally, data node 1 will push 3 acknowledgement, including its own, into the pipeline and send it to the client. The client will inform name node that data has been written successfully. The name node will update its metadata and the client will shut down the pipeline. Alright, so as we talked already. So now see one thing, it may so happen that name node will ask to write to different places first. So there are 2 blocks that we want to write, say, simultaneously. So these 2 blocks will be written simultaneously. Alright. So into the first node, they will be written simultaneously. Say my first node for block A is data node 1. My first node for block B is data node 9. Say okay. So both these will be written in parallel. Then the copy will take place sequentially. So we can see here block A goes through the core switch to data node 1. And from data node 1 to data node 6 and from data node 6 to data node 8. So 1A to 2A, 3A, 4A, 4-step process. Compare that to the process for block B. It goes through core switch to data node 9 and from then data node 9 to data node 11, then through the rack switch and through this core switch to this rack switch and finally to data node 3. Alright. So this is what is happening. So this is a 6-step process, this is a 4-step process. Okay. So parallelly they were written. So first block were written parallelly, but then sequentially it took one pipeline took longer time, another pipeline took shorter time. Okay. So parallel data blocks are written parallelly to the first data node, and then the first data node will sequentially write to other data node, replicate to other data node. Okay. So this is what it is. The client will copy block A and block B to the first data node simultaneously. Therefore, in our case, 2 pipelines will be formed for each of the block, and all the process discussed above will happen in parallel in these 2 pipelines. The client writes the block into the first data node, and then the data node will be replicating the block sequentially. The flow of operation that is taking place for each block in their respective pipeline is this: 1A, 2A, 3A to 4A for this first pipeline, and then for block B it is a longer pipeline, right? So yeah, don't think that's just because we are replicating it 3 times, each of the block 3 times, so it is going to take equal amount of time for each block. Some block will take a larger amount of time, some block will take a smaller amount of time to be written. All right. So next is reading. Okay, so say I want to read some file. Okay, example.txt. So I will tell name node that I want to read some file. Okay, name node will tell me that your file is divided into 2 blocks, A and B, and you can read this A and B in from data node 1 and data node 3. Okay, then we will go through the core switch, and we will go through the rack switch to data node 1 and data node 3, and then we will read these 2 blocks from data node 1 and data node 3 through the rack switch back to core switch to the client. Alright, so this is a very simple pipeline to read a file from this distributed file system, from this HDFS. The client will reach out to name node asking for the block metadata for the file, say example.txt. The name node will return the list of data node where each block is stored. After that client will connect to data node where the blocks are stored. The client starts reading data parallelly from the data node. Once the client gets all the required file blocks, it will combine this file block to form a file. While serving read request of the client, HDFS selects the replica which is closest to the client. This reduces the data latency and the bandwidth consumption. Therefore, the replica is selected which reside on the same rack as the reader node if possible. So yeah, this is one more thing. HDFS will do what? The client see, data blocks are replicated across the cluster, right? So one of this machine in the cluster will now try to read the data block. So is name node will do what? Name node will provide the data node which is closest to the reader. Okay, if possible, then name node will assign a data node which is on the same rack as the reader. Okay, that will reduce the latency to a great extent. So yeah, this is a optimization that is available in HDFS. All right, so when serving data request, the closest data node in which the data is available is provided. So yeah, this is how read is done. All right, so yeah, this is all about HDFS. We can put data in HDFS. We can read from HDFS through simple command line instruction that we have. There are commands that we can run, very simple command to put and read data from HDFS, right? Behind the scene, HDFS will use all these pipelines, all these methods to read and write the file. So this is not something that we should be concerned as a user. Okay, these are nothing of our concern. We will simply write this file to HDFS or read this file from HDFS. This entire mechanism will take place behind the scene, and this is nothing of our concern. Okay, so this is a very beautiful system that is given to us, a distributed file system that spans across multiple machine. We don't need very high-end machine, although we can use high-end machine. Even commodity machines is sufficient to create our cluster. Even if our machine fail, one machine fail, it is not a problem. Our data will be available in some other machine. Okay, our name node knows what are the machine data available. If some machine goes down, our name node will know that a machine has gone down, and then we will arrange all these different machine, our computers, in racks. So even if the power failure occur in a rack, okay, still we will have data access from some other rack. So this is a very redundant, this is a very good architecture that Hadoop gives us. Okay, HDFS. Next, once we have finished writing our data, all right, once we have finished storing our data, we can now store data, we can read data from this distributed file system. The next thing is processing this data. Okay, for that we have Mapreduce. Mapreduce is a programming model and an associated implementation of processing and generating big data sets with a parallel distributed algorithm in a cluster. So one good example that is given is this. Say I have this main election office and I have this different election booth. Okay, traditionally what will happen is from all this election booth, my election data will be sent to the main office, and in main office I will have to count all this different election result from all these different booths, right? So the pressure on the main office increases a lot. All right, so only in one place we have to do all this calculation, and then that one place will be overwhelmed with all this work that it has to do. Okay, but then this is the traditional approach. In traditional supercomputer, even what would have happened, our normal supercomputer would do this. You will have data in different places, the data will be brought to the supercomputer, and then that computer will have lots of processor, granted it will have many processor. Now in that computer only our entire processing is going to take place. Okay, so that computer is going to get overwhelmed. Now compare that to Mapreduce process. In Mapreduce, what is going to happen? Going back to our election analogy, okay, in each of this election booth they will do this counting. Okay, so say I have 5 booths. In each of the election booth I will do this counting. Okay, once counting is done, I will just send the result of each of the booth to the main election office, and in this election office only summation will take place. So majority of the counting is done at the election booth itself. All right, so the amount of work that was being done at the election office, that reduces to a large extent. Okay, so this is what we have. This is the Mapreduce approach. Okay, in Mapreduce approach compared to your traditional approach, our data, because of HDFS we know our data is scattered in lots of different computers throughout the cluster. Okay, now instead of bringing the data to one place and processing it, we will send our program to all these different places, and the program will execute at those different places and send back the result to me. Okay, so processing is moved to the data unit instead of data being moved to the processing unit. So this is Mapreduce. Okay, so in Mapreduce there are basically three core works that need to be done. One is map, next is shuffle, and finally reduce. In map, what will happen? Each worker node applies the map function to the local data and write the output to a temporary storage. A master node ensures that only one copy of the redundant input data is processed. An example of mapping is this. We will sort, say I want to count, look at what is the frequency of names of student. Okay, so of first name of student. So what I will do, I will arrange all these different students in different lines, okay, based on their name. So all the students with name Jack will stand on one line, all the students with name Jill will stand on some other line. All right, so this process of making all the students with name Jack stand on one line, all the students with name Jill stand on some other line. All right, this is mapping. Okay, then we have shuffle. All right, so we will look at this with far better example. All right, so worker node redistribute data based on output key such that all data belonging to one key is located on the same worker node. Okay, then this will happen. Going back to our example, Okay, say I want to find a frequency of all the students in frequency of first name of all the students in our college. What I will do, now in each department, okay, I will make, say in computer science department, all the students of with name Jack will stand in one line, all the students with name Jill will stand in another line. Similarly in mechanical department, all the students will name Jack will stand in one line, all the students with name Jill will stand in another. Similarly in civil department, same thing will happen. Alright, now this is mapping. Next is shuffling. In shuffling, what will happen, all these students from all these different department, okay, with name Jack, they will be brought together and made to stand in one place. Okay, previously it was department wise, now all of them will be brought together with name Jack, all the students name Jack will be together, all the students name Jill will be together. So from all these different places they will be made brought and made to stand together. And finally reduce. In reduce, what we will do, we will actually count the number of students. Alright, so reduce worker nodes now process each group of data per key in parallel, now such as counting the number of student in each queue. So that will give me the frequency of the different first names. Okay, so this I hope I will be able to explain with this example. What will happen, my data, okay, will be split into key value. Okay, then I will have, say for key 1 I will have some value, I will have key 2 some value, key 3 some value, again key 1 some value, key 2 some value. So my data is in different data nodes, right? So in data node 1 I will have key 1 some value, key 2 some value, key 3 some value. Similarly data node 2, key 1, key 2, key 3, and so on. So this is what map will do. Then what will shuffle do, all these different data node, this key will have this key 1 and value, right? So for key 1, from all these different data node, the values will be brought together. Okay, then similarly key 2, key 3, for all the key 1 the values will be brought together. For key 2 all the values will be brought together. Now finally this will be reduced to create our final output. Let me explain this with yet another example. Let us say I have this text, Bagisa mane fuloni, fuloni mane bagisa, bagisa bagisa fuloni. Okay, so I have 3 lines in this file. Okay, this is a famous song, a song that became relatively famous recently. Okay, so I have these 3 lines from this song. The third line I made on my own. Okay, so what will I do? First, the split of the data will take place. So here I have data in key value pair. So first I have key 1, that is my line 1, bagisa mane fuloni, 2 fuloni mane bagisa, 3 bagisa bagisa fuloni. So I have this data that is split and put in different blocks in key value style, right? Then what will happen? Mapping will take place. Now in mapping I will do this. I will take bagisa equal to 1, mane equal to 1, fuloni equal to 1. Okay, this will be given and my mapping will make a list of key values. Okay, so bagisa 1, mane 1, fuloni 1. Here I am simply counting. Okay, and counting with this restriction. I will make the final count later on. Here each time I am reading a word, I am writing that word and then a 1, because I am seeing that word once. Then again bagisa fuloni, I am seeing bagisa once, I am seeing bagisa once again. I am not writing bagisa 2 right now. Okay, counting I will do later. Right now I am just making this key value. So bagisa 1, once again bagisa 1, and then fuloni 1. Now in shuffling what will happen? All this key, bagisa, mane, fuloni, all this bagisa is here, right? All these values from bagisa from different places will be brought together. Okay, so bagisa 1, 2, 3, 4. So from here 1, 2, 3 and 4 they are brought together. Mane from here, here and here, from here and here they are brought together. Then fuloni from here, here and here they are brought together. Okay, so Bagisa, finally all this for one key, the different values that I have are brought together. Okay, this is what is happening in shuffling. Then finally in reducing, I am counting all these different values that I have, and that is how I have the total. Okay, so after shuffling I have my final output. Okay, so this is how, using the Mapreduce paradigm, I can count the frequency of each word in my text. Alright, so this is what I have. Now here is a some part of the total code. Okay, my entire code will be lot bigger than this, but I have taken out some part from the code. My map is going to do what? My map is going to get these lines, these different splitted lines, and each of these lines I am going to split further into words, and then each of the word I am going to write the word, and I am going to write 1. Okay, output value is 1, so I am going to write the word and 1. So I have read this Bagisa Mane Fuloni. I have split it into Bagisa, Mane and Fuloni. I am writing Bagisa 1, Mane 1, Fuloni 1. Alright, so that is what I have done. I have taken the line, I have split the line into all these different words, and then finally okay, there is a mistake, it should be space, not comma. Okay, and then finally I am outputting each of the word into value. Okay, so key value in the form word 1, word 1. Okay, so word, what is my key? Key is the word, and then what is the value? Value is 1. Okay, that is what I have done. That is my mapping process. Finally, then I have this reduce process. In reduce, I will get what? I will get this as the input. Okay, so one key and then the list. Okay, so what I will do for that key, I will do this. I will iterate through this list and add the values in the list. So for this key Bagisa, okay, I will iterate through this list and add the values. So 1 plus 1 plus 1 plus 1 will give me 4. So that is what I will do. I will have sum equal to 0, and then for I will add all these values in the list. Then what I will do, I will give the word that I had and what is the sum that I have. Okay, so Bagisa was the original word, then I counted 1 plus 1 plus 1 plus 1, so I got 4, and then I outputted Bagisa 4. Okay, so Bagisa 4. So this is how I have counted the occurrence of this word Bagisa, and finally here I have Bagisa is equal to 4, Mane equal to 2, Fulon equal to 3. This is my final output after this reduce. So this is my code. In my code I have this map function and the reduce function. In map I will have to write this inside a class. Okay, this is not a complete program. This is not the complete program. I will have to write lots of other things, especially this map I will have to write inside a class that will have to inherit another class called mapper. This reduce I will have to write inside another class that will have to inherit another class called reducer, and then I will need a class that will have a main function that will have some configuration, alright, for Hadoop. So my aim is not to show you the entire configuration of Hadoop. My aim here is to show you how to write the map function and the reduce function, okay, to count the number of words in a text. Alright, so this is what I have. Okay, so this is how Mapreduce works. Alright, let us now talk about using Mapreduce to do analysis of data. Alright, so first thing, there are lots of data analysis algorithm. We will be looking at them at a later time. Today I am going to show you a very easy algorithm in data analysis. This is called Nearest Neighbour. Okay, it is a non-parametric, so it does not depend on any probability distribution or any kind of distribution, and it is used for classification and regression. Essentially what we have, lots of different data points. We have this red data point, we have this blue data point, and we have this green one. Okay, now I have to tell, we have to know what is this green one. Is it red, is it blue? So how will I know? I will be looking at a certain number of neighbors. I will be looking at k of my nearest neighbor. Okay, so here k is equal to 3, so I use k equal to 3. I look at 3 of my nearest neighbor. These 3 are my nearest neighbor. 2 of them are red, 1 is blue, so I know most of my neighbors are red, so I am saying that this green is also red. I am also red. Okay, that is what is this circle? This circle is also red. Okay, now look at this k. What will happen if I increase the value of k? If I increase the value of k to 5, now I have 2 red neighbors, I have 3 blue neighbors. Okay, so now I will say most of my neighbors are blue. I will say that I am blue. Okay, so this is how k nearest neighbor works. Based on the different value of k, we will have different output. So if we have 2 less k, we may have we may have this thing. We may be susceptible to noise. Noise may influence our decision. If our k is too big, then we become too general. We will have underfitting of data. Okay, so this is what will happen. We have to get some very good value of k. Okay, so k nearest algorithm, very simple. This is the pseudocode of k nearest algorithm. So what will we do? We will have this xy, where x is training data, y is the class level of x, then this small x, which is some unknown sample for which we have to know its class. What do we do? For all these different training data, we compute the distance of each of the point from this unknown point. Okay, then after computing the distance of all of the point, we take the 3 or k nearest points. Okay, so among these k nearest points, we will do this majority voting. Which class has the majority? Okay, once we get the majority, the class which is occurring the most number of times among our k nearest neighbor, we will say that my current class is that class. Okay, very simple. Now runtime of is n into d, where d is the number of feature, n is the number of training instances. So this is the complexity of running k nearest neighbor. And then we have a large memory requirement. So our entire data, okay, has to be in memory. We have to, for each classification, each prediction that we want to do, we have to go through all this training data. Okay, this is unlike, say, other methods, say like random forest or deep neural network. In random forest, we don't need to go through all this data when doing this classification, right? We will, from this data, we will create a tree, and we just need to keep the tree in memory. Okay, we just need to go through the tree to do a classification. In deep learning, we will have a series of metrics, and this matrix we need to multiply, and then we will get this new class. All right, we don't need to keep the entire data in memory. But in KNN, we have to go through all this entire data. We have to calculate the distance from each of the data point. So we need to keep all the data in memory. So if my data is bigger than the memory that I have, okay, so this is going to cause problem, right? So this is what we have. Memory consumption is also a problem in k nearest neighbor. So here is an example of k nearest neighbor. I have these 9 data points. This is from some a data set called iris. So there we have iris flower. So we have sepal length, sepal width, petal length, and petal width of different flower. So I have 9 different flowers. This scientist, some scientists, they have measured all these parameters, sepal length, sepal width, petal length, and petal width for different iris flowers. Okay, so iris flowers have 3 species: setosa, versicolor, and virginica. So what is happening? So with 5.1 inch sepal length, 3.5 inch sepal width, 1.4 inch petal length, and 0.2 inch petal width, I have a flower, and this is setosa. All right. So this another flower has this measurements, and this is versicolor, and yet another has this measurement. This is virginica. So this is what I have. I have the measurement of these parameters of flowers, and then I have here recorded what is the flower. So like this, I have 9 training data sets. Okay, this training data set I am saying this are TR, I am denoting by TR. Okay, then I have this test data set TS. Here I am given this measurement, but I don't know what is the class of these flowers, what is the species of this flower. So I am going to use Knn to figure out the species of these 3 flowers. Okay, so one more thing I was talking about how to find my neighbor. Okay, so there are lots of way to find neighbor based on distance. Okay, so how do we find distance? So the one who has the closest distance to me is my closest neighbor. So there are lots of ways to find distance. In this video, let us look at one of them. This is the Euclidean distance. Essentially, the way to find distance between 2 points that you studied back in school, x1 minus x2 whole square plus y1 minus y2 whole square. You will do this for as many dimensions that you have. Here we have 4 dimensions. Okay, so this is a x1, x2, x3, so x, y, z and w say. So x1 minus x2 plus y1 minus y2 whole square, x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square plus w1 minus w2 whole square. So we will have this sum, and then we will have this root over of this sum. Okay, that will give me Euclidean distance. That is the distance on your what do you have, coordinate, Cartesian coordinate axis. Okay, along this Cartesian coordinate space that you have, Cartesian space that you have. All right, so the distance between 2 points in Cartesian space, Euclidean space. So this is the formula. All right, so with this I can find the distance between, say for test this test data set, okay, TS1, I can find the distance between this and all this, say TR1. So how will I find? I will do 4.6 minus 5.1 square, 3.1 minus 3.5 square, 1.5 minus 1.4 square, and 0.2 minus 0.2 square. Alright, I will get something, and then I will have a root over of that. That will give me the distance between TS1 and TR1. Okay, so this is how I will find the distance between TS1 and all this TR1 to TR9. I will find the distance between TS2 and all this. I will find distance between TS3 and all this. So this is how I will find the distance between all of my test set and all of my training set. Alright, then after this distance is found, I will do this. I am trying to find 3 nearest neighbor, my k nearest neighbor, where my k is equal to 3. So what will I do? I will write down my 3 nearest neighbor, the nearest, the second nearest, and my third nearest for TS1. So for TS1, TR3 is my nearest. Alright, TR2 is second nearest, TR1 is the third nearest. So what I have written down, I have written down the class of TR3. Okay, so the class of TR3 is setosa. Okay, class of TR2, class of TR2 is setosa, class of TR1, class of TR1 is setosa. So I have written for all my 3 nearest neighbor over here. Okay, I have written the 3 nearest neighbor, and I have written the distance in increasing order. Alright, this is my nearest, second nearest, third nearest. Similarly for TS2, their nearest one is this one, TR8. TR8 is Virginica. Okay, then second nearest is TR6. TR6 is versicolor. Okay, then third nearest is TR9. TR9 is Virginica. Okay, so this is how I have for TS2, my nearest neighbor is a Virginica, second nearest is versicolor, third nearest is Virginica. Okay, and similarly I have for TS3, the nearest is versicolor, second nearest is Virginica, third nearest is versicolor. So this is how this same table I have written over here, the nearest neighbor, the second nearest neighbor, and third nearest neighbor. So for TS1, I have looking at 3 of the neighbor, all 3 are setosa, so I know TS1 is setosa. Similarly for TS2, I am looking at Virginica, my 3 nearest neighbor, 2 of them is Virginica, 1 is versicolor. So most of my neighbors, maximum is Virginica, so I am saying my TS2 is Virginica. Similarly TS3, I have 3 neighbors, nearest neighbor, 2 of them are versicolor, 1 is Virginica, so I am saying that my TS3 is versicolor. Okay, so yes, this is Knn algorithm. So in Knn algorithm, what we have done, we have calculated the distance from any given point to all the training data set that we have. Okay, from unknown point to all the training data set, and then we have sorted this training distance from training data set in ascending order. So the nearest, second nearest, third nearest, so the k nearest I will take. Okay, so here k is equal to 3, so I have taken 3 nearest of my neighbors, and then I will be looking at what is the class of all this nearest neighbor, k nearest neighbor. The class that occurs the maximum number of time, I will say that my unknown data set is of that class. Okay, simple algorithm. Now we saw this algorithm has 2 problems. One is the runtime, that is n into d, and another is with a large data set we need to keep the entire data set in memory, and so this is going to be problematic when my data set is larger than the RAM itself. Okay, so what do we do? My data set, if it is too large, I cannot keep on one drive, so I will be using Mapreduce to run k nearest neighbor. Okay, so in Mapreduce, what will I do? My test data set will be split, okay, and will be in different computers, different data nodes, and then I will make this for train data set. I will make this matrix that I had made, this matrix. All right, this k nearest neighbor matrix. So what will I have? I will have k columns and t. Since I have 3 data set and 3 neighbors, so k neighbors and t number of test data set. So t into k. Okay, so among all this training data, I will find the k nearest. Okay, from in all this training data, I will find the k nearest for each of the test data point. Alright, so this is how I will have partial k nearest for all this partial data. Okay, now this is the thing that we are going to do. We will compute all this partial nearest data, so nearest distance matrix we will calculate. Okay, then this will take place in the map phase. In the reduce phase, what is going to happen? In the reduce phase, first we will keep a blank or with random value we will create this t into k, t test data points and k number of neighbors. Okay, so t into k matrix we will have. Now we will combine all these different matrices to create this distance matrix. So I will give you the algorithm how this has to be done, but then think of it this in this way. For say test data 1, okay, test data 1 and test data 1, what will I have here? I will have ignore all this other. Okay, I am talking only about test data 1. So here I am going to calculate my k nearest neighbor from this part of the training set. Okay, so k nearest from here, here I will have k nearest from here, here I will have k nearest from this part. Okay, so say how, let me give you an analogy. Let me think about an analogy. Okay, say somehow you are trying to find your nearest so the person you like the most, the friend you like the most. Okay, so you go to computer science department, and you are trying to make a list of 5 friends that you like the most. Okay, now you go to computer science department, you calculate your likeness factor among all the people in the department, and then you sort it, this list. Okay, the one that you like the most, then the second, third, fourth, fifth. From computer science department, you are taking 5 names. Okay, these 5 names are sorted in who you like the most, second most, third most, fourth most, fifth most. Okay, and you have given some value of how much you like that person. Okay, this is a sorted list. Then you go and make this list in civil department. Okay, and similarly you get 5 people from civil department. Now you have 5 people from computer science department, 5 people from civil department. Okay, so from partial data from computer science department, you have this 5 nearest from computer science, 5 nearest from civil department. Together you will combine and you will get 5 nearest from both this department. Okay, how will you do? From this 5 and this 5, you will merge them together. You have seen this already. If I have 2 ordered list, okay, of say n length, and I want to merge them together, okay, this is going to take linear time. Okay, and we did this in merge sort. In merge sort, when we were combining these sorted arrays, okay, we had this n by 2 array and n by 2 array, we merged them together and formed a n length array. So that took place in linear time. Okay, so we know that merging to sorted array and creating a sorted array from this merged array is going to take linear time. So what am I going to do? From my computer science department, I found my 5 nearest k nearest neighbor. From my civil department, I found my k nearest neighbor. From mechanical department, I found k nearest neighbor. Okay, so I have this list of k people from civil, k people from computer science, and k people from mechanical. I can do one thing. I can take these arrays and I can merge them, and I am not going to have this entire k plus k from these 3 departments, right? What am I going to do? I am going to have the k nearest neighbor. Okay, k people that I like the most among all these 3 departments. Alright, so since it cannot be anyone other from all these 3 lists, like I am going to find 5 people that I like the most. So 5 people from computer, 5 people from mechanical, 5 people from civil that I like the most, I have individually collected, and then the 5 people overall that I like the most is going to be from this itself, right? So it cannot be apart from this. Or say I have only 3 departments in my college. Alright, so this is what I have. So when I merge them together and I take only k out of this merging, alright, so if I take 5, 5, 5, if I merge them together, I will have a sorted list of 15 people. Okay, I don't need this 15 people, I need only 5, since I am looking at 5 k nearest neighbor. Okay, I am trying to find a list of 5 people that I like the most. So this is what I will do. Okay, so this is what has happened. I hope I have been able to explain what I am doing. So this partial k nearest neighbor I figured out for all this partial training data set, and then I merged them together to find the total k nearest neighbor. Alright, so I explained with one data set, the same thing is going to happen for I explained for one training set, the same thing is going to happen for all these t different training data set. Okay, so in mapping I did this partial calculation of who my neighbors are. Then from that in reduced stage I created first a empty random t into k matrix, and then I filled the matrix by combining all these different partial distance that I had, and that is how I have a total k nearest neighbor of the total data set. Okay, now I have this total k nearest neighbor over here, and then using majority voting like we did from this, okay, we can do our final prediction. Okay, so this is what will happen. So mapping, and then reduce is divided into 3 steps. One is setup, one is reduce itself, and then the cleanup after reduce. Alright, So this is what we have. So this is how we do Knn using this Mapreduce paradigm. Here is the algorithm of the map function. In map function, we will for this training data set must be available everywhere. Okay, so test data set will be split, but the train data set will be split. The test data set will be available everywhere. Okay, so for test data set, we will have this thing. We will calculate this neighbor, and then for each j, we will give this partial matrix. Okay, in reduce, we will combine these different partial matrix to create one new matrix which will have data from all these different partial matrix. So all these partial matrix will also be t into k. Okay, so from civil department also I got 5 people, from computer also I got 5 people, from mechanical also I got 5 people. But then by combining them together, and after combining, finally I got 5 people. Okay, it's not that now I have a list of 15. I don't want a list of 15. I need a list of 5 only. Okay, so 5 people that I like the most. That is what I wanted. So from here, this partial I got t into k. From here also t into k. From here also t into k. But then after combining, I still keep t into k. I do not keep I do not combine all the things and keep more than this size. Okay, so I don't keep t into k plus k. Alright, so this is what I have. I combine in the reduce stage, and finally in the cleanup stage I do this majority voting, and that is how I make the prediction. Okay, so go through the algorithm. Very simple. I hope you understood this Knn. Knn, if you did not understand, go through YouTube videos. It's a very simple algorithm. Okay, the most simple algorithm in data analysis. Non-parametric, lazy learning. Lazy learning in the sense that we do not learn anything. Like in deep neural net, we will be learning a few matrices. In random forest, we will be creating a tree. Sorry, in random forest will be creating several trees. Okay, and we will be using this tree or this matrices at a later point of time. Unlike that, in Knn, we do not create any such summary of data. Okay, we have to go through the data. We have to figure through the training data. We have to go each and every time for each point. We have to figure out the distance from each data. We have to sort it and find the k nearest neighbor, and among this k nearest neighbor, the class with the majority label, we have to pick that and say this is my predicted class. So we have to run this entire process for each and every training data point. Okay, so this is simple to understand. Okay, compared to all these other processes that we have. And in this video, my aim was to show you how to run this k nearest neighbor using this Mapreduce paradigm. Okay, so apart from k nearest neighbor, we have lots of other algorithms in data analysis. We will be looking at all these different algorithms in the next video. In our next video, we will also be looking at one more module of Hadoop called Mahout. Okay, so that module helps us in doing data analysis. So these things, this Mapreduce based Knn implementation that we saw, we don't need to do this. All these are already built into Hadoop. We just need to use these things and run on our data and do this prediction, regression, classification. We will be talking about what these things are, what is classification, regression, what are the different things that we can do in data analysis, how to evaluate whether the analysis that we have done, is it a good analysis, or does this analysis have lots of errors. So we will be talking about all these issues in the next video. I hope this video was interesting for you. Okay, in this video we first talked about how IoT is increasing that data. Okay, and then we talked about big data, what is big data. Then we talked about Hadoop. Okay, in Hadoop we saw HDFS, which is Hadoop distributed file system, and then this Mapreduce paradigm of programming large data, and then we saw what is KNN, and finally we saw how to implement KNN using Mapreduce paradigm. So I hope you understood everything in this video. If not, you can of course WhatsApp me, you can mail me, or you can write your doubt in the comment section below. Thank you for watching this video. See you in the next video.